Project report is due on Monday. So in doing that, even if it's a group of more than one person, which almost all of them are, you should make sure it's one coherent document. I want kind of one story. I don't want a few different pieces kind of stapled together. I know a lot of you broke it up into different pieces, and you kind of have different components to it. That's great, but make sure it's one coherent thing. It's 4 pages per person. So if you go, you can have like an appendix with more stuff in there, but don't input anything important in there. Don't put like your chart with all of your data in the appendix and then I can't see it. Only in the first 4 pages per person is it going to count towards a grade. Okay, if you want to show you did it, you can put it in there, that's fine. But the first 4 pages. And there's also, so a few of you like to use small margins and small font. I think I actually wrote into this one that there's that it has to be at least 11-point font, and don't make the margins too small either. So can everyone hear me if I'm speaking like this? Is this is okay? Sorry. So okay. So I'll try and stay kind of excited, and I'll speak a little bit louder, I guess. All right. All right. So talk about MapReduce. So has everyone heard of MapReduce? Yeah. So who's used some form of MapReduce? Okay, so a few of you have used it. So I may not, teach you too mumuch more, but we'll talk about the kind of the fundamentals behind this as well. All right, so MapReduce, we talked about PageRank on Monday, and that was some technology developed at Google that helped them have their search engine be kind of more effective than any other search engine. It's really influenced that. So this was more of a systems technology that they had that is a widely used kind of tool for a lot of the very large data sets they have. So one of the issues is they have really large data sets, and you need many machines to process these. And if you've ever tried programming in something like MPI or one of these parallel programming environments, it's really tricky. It's it's like if you program in Java versus in C. There's more things you have to do in C to get right. You have to worry about the memory. You can't rely on the garbage collector and so forth. So when you go to a parallel algorithm, it's similar in most ways in that you have to worry about getting all the machines to work together. If one machine fails, and there's all sorts of these issues that you have to worry about. So MapReduce was a way to try and simplify all this and let kind of the back end take care of all those details, like say like the garbage collector in Java. Okay, before we talk about MapReduce itself, I just want to talk a little bit about big data. So this is really, so these two things have for a while we're very synonymous. When people thought of big data, they thought about MapReduce. So things have kind of evolved at the system level past MapReduce, and we'll mention some of the ways, directions it's gone past that. But so if it's about to blow over, tell me. So start waving or something. So this is really a story about you have lots of data, and not only is it just big, like we've had data which has been hard to deal with because of its size for a long time, but there are other kind of properties which were consistent about it, which allowed you to have a more simplified structure, which is the MapReduce on top of it. Right. So the first thing was the data was fairly static, so it's not really changing very much. You get big data, you get a large amount of data, and then it's not like you're going and updating all the time. This data took you a long time to collect. this was like running a crawler on the whole web for several months, and eventually, after you've done this for a while, you have your data set. You're not going to go and update. Now, there are going to be some updates, but the updates aren't going to happen all that often. And most of the updates, the updates are, I didn't spell that nearly right. So most of the updates are appends. You're kind of just adding data on. You're not going back and changing stuff so much. You're more just saying, there's new web pages I found, right? I'm keeping track of the data set. I've got more data. I keep collecting this. And so this will be kind of easier to work with. So we don't have to go back and change what we had before. We just have to add new stuff. So the second thing is this data is really enormous. So, for a lot of data analysis for a lot of companies, their data they could set up some one, say, powerful server and one big database, and they could just put all of their data in there, and that was all they needed. Now, the data is so big it may not fit on any one machine, or maybe you can buy a really powerful machine, but it may be simpler if you just had 10 or 100, just plain commodity machines. If you go to Dell and you buy some computers, you would just buy the regular computers, and this would be, you'd rather just use these. But it can go up to 10 to 1,000. In some cases, some of the data sets that Google has, I've heard, are on things like hundreds of thousands of computers that spread across them. It's so big. Okay, so there's lots and lots of computers, not just one computer. So you really need to think about doing the computation not just in one place, but distributing this computation. Okay, and we're somehow going to move the computation to the data, whereas a lot of the computer infrastructure and architecture is moving the data to the processor where the computer is. We're more moving the computation to the data now instead. Okay, so these were true definitely of the problems that Google had internally, but this is also true of this larger phenomena which has been going on called data science. Okay, and so to kind of explain what data science is. So you have to think about what is science, right? So if you think about the scientific hypothesis, right? So who's done a science fair project? Yeah. So when you do a science fair project, what are the steps of doing science? Like, what were you taught?
Asking for like the scientific process.
That's right, yeah. What's the scientific process?
Like observation, hypothesis, test.
Yeah, good.
Do it all over again.
That's right. So if you just do science, you're going to do step one. So you make some sort of hypothesis. Maybe you have some observation first before you make this, but you make some hypothesis about the data. So after you make the hypothesis, you need to go and collect data. You need to go and observe stuff. So if you go back to the days of like Mendel, I think it was Mendel who did like the early. What?
Periodic.
Was it? Oh, so he did the periodic table. Who was the monk who did like the experiments with the kind of breeding of plants and stuff? So anyway, so people would go and what? Yeah. Okay. So let's say Mendel. Okay, whoever it is. Some guy in the 1800s. They would do experiments. They would make some hypothesis. They'd go and gather data. They would grow plants and observe them. They would go and collect. They'd get like 100 data points, right? And then once they have the data, then they'd say, then they would do some form of test. Maybe this is some sort of statistical test, some way of evaluating whether the data they've gathered validated their hypothesis. And if it did, then they said, this is great, I've learned something. And there are issues about having controls and all this sort of things. But sometimes it turns out your test was wrong, and this was more often than not actually. And so then you have to go back and make this new hypothesis, right? Okay, so this was science and has been for 100 or so years. And we've done great stuff with this, but this method of doing science is really dying. This is not largely how people do science anymore. They're moving to this paradigm of data science. And if you notice, if you repeat this over and over again, every time you do it, you're gathering data, and at the end, you have this big data now. You've gathered this data, you've been doing this for a long time, and so now you have this pre-existing data set. People are being much better at sharing their data. It's available online and at collecting large amounts of data. So now, instead of first forming a hypothesis and then gathering it and then testing it, we already have the data. So we just want to try and do some data mining and find some valid structure inside of the data. Right? So we want to somehow just directly find the structure, and that's kind of what this class has been about in some sense, right? Starting with the data and then finding the structure directly. Hopefully, you find it in a way such that it's going to be statistically viable. That it's fair. There are other things you have to worry about now about like the multiple hypothesis testing. If you look at it multiple times, you're going to keep looking until you find something that looks like it's significant. And so I haven't really talked about p-values and so forth in this class. They're kind of very dangerous in this setting. And it's not totally exactly understood how to actually validate something under this model. This is kind of still an open question. Okay, so getting back to MapReduce. So when you think of having this data and it fits in this big data model where it's static, you're only appending to it by gathering more data. And it's enormous, it's now really big, it may not fit in the memory anymore, or at least not the memory, it's on multiple machines, then MapReduce is going to be a tool that will be useful for processing this, and it's a kind of a restricted, simplified way of doing that, and it's really tuned, and it's kind of corresponds with this data science view of the world. Okay. So any questions on this while I'm erasing? All right, so before we can talk about MapReduce though, it's actually important to think about how is the data stored. And this is actually some work that came before and MapReduce was built on top of. And so this is the idea of a distributed file system. Okay, so this is called different things in different locations. So inside of Google, this is called the Google file system. Hadoop is essentially one of the dominant open source versions of MapReduce, and there's called the Hadoop file system, the HDFS. So if you may have heard of this, it basically works in a certain way. So it's kind of in contrast to how things typically work in a more traditional database. It's much more freeform. It's much less structure going on there. And so data is stored in these actual important amount of the information is in this part, which is the value. The key is some sort of identifier. Sometimes it's a unique identifier that lets you tell you what the data is, and then you just store it. So it's a very flexible format, and we'll talk about, it's a little too flexible to do anything with by itself, so MapReduce will kind of take this and do something with it, okay? So some examples of this is where, so it's where like the key is like a log ID. If you have logs of some process you've run, they usually have some unique ID you can refer to, and then the value is just the log that you've stored there. Okay, so another example would be like if you're thinking of storing the entire web, and Google probably has several copies of the web and its servers, then each of the keys may initially be just some identifier for the page. This could be its address, its HTTP address, or some other way of identifying it. And then the value may be the content of the web page, right? All the text on the web page, or maybe all of the links in the web page. You may slightly refine it, okay? But at the basic, you're more likely going to have more information. You may just have the full copy of the web page there. So keep in mind, this is data we've collected. We're going to do many sorts of types of analysis on top of this data. And we only want to store it once, so we'll store it once in this system, and then we'll access it and do different things with it. So we may want to store more in the value than we'll need for many of the questions we're going to ask. Yeah, so so another example of this is like you may store like a word or some sort of identifier. So I told you about when you have the search engine, when Google has this, they aren't re-searching the web every time you have a query. They have this built already. So if you have a keyword that you search for, they already have, say, the page where this word is on that you've searched for, or some other identifiers about this word that will allow you to refine something. So this may not be the initial way it's stored, but this is another representation inside of a key value pair, right? So the backend may store it in this way, and then you may want it in this way so you can answer search queries very quickly. But it's still this key value pair representation. So it's very flexible. You can actually encode structure inside the value part. So if you want to, go into it and get it later, you can. So the value can be pretty much anything, and the key is some sort of identifier. And it may not actually be a unique identifier. This word may appear in many different locations and may have many things associated with it. So you may have many key value pairs with the same word. All right. Okay, so one of the nice things about when you're working with MapReduce is you only need to think about data in this way. You can just think it's these key value pairs, but that's not actually how it's stored. The full part of the storage system. If you just had these scattered all over the place, the system would not be as robust and would have certain issues with it. So you have another kind of a hierarchy of structure here, and this is kind of the lowest level that you really have to think about. But what's going on internally is you have actually this block structure. So you're going to think of taking chunks of these key value pairs and grouping them into these blocks of about roughly, some size. Maybe it's going to be a 64 megabytes. So that's kind of the rough size I've heard is that's typically used. And so you kind of take these and you break them down into these. You combine them together in these pieces. Now it's possible that just the value, if it's like a really long web page, it may be bigger than 64 megabytes. In that case, you can split it over several blocks. And so you would think of the word as 64 megabytes of information, and then you would put a link to into the next block that it's in. So you can break up key value pairs if you need to, but you try and keep this as a coherent set of these if you can. Okay. So it's not just. So the second thing is that. So these blocks are not just stored once. Each block is then replicated 3 times. So it's, there's some parameter here. It could be 2, could be 4. I think it's often that they replicate it 3 times. In some smaller systems, I know in our system that we're running, it's only replicated twice. Just because it takes up less space. So when you're doing this, you're increasing the size of the data by a factor of 3. But you know what? It turns out storage is actually fairly cheap. So if you're running one of these big companies that has all this data and you're doing it correctly, you're probably making lots of money and you can afford to replicate your data 3 times. In fact, one of the points of this is you're storing it in some format, so you're going to access it and query it in many different ways. If you weren't doing it in such a flexible format, you would probably be replicating it just so you had it in these different formats that you would be storing it anyways. So now I'm just storing it once in this general format, but then replicating the structure 3 times. And then these 3 replications. These are the different replications. The blocks are going to be stored on different computers. Okay, and maybe you have a sense of neighboring blocks if you have a sequence of data. The neighboring blocks do not need to be on the same computer. In fact, they try and put them on different computers. So you're essentially going to say you have a set of computers that's storing all of your data, and you kind of want to put it randomly. You want to spread them out as much as possible. So 2 blocks are not likely to be next to each other. So sometimes you want to have maybe 1 copy of each block so it's near another one. Maybe not the same computer, the same processing engine, but maybe on a nearby one on the network. So if you're really dealing with 1,000 computers, some of them are going to be closer to each other in the network space. And you may think a little bit about this, but but these issues are kind of taken care of in the background. You can think of them as basically being far apart. Okay. Okay. So if there's so given this, we're replicating it, but then we're putting the replicas, we're putting nearby blocks far away. Hopefully, this should seem kind of strange to you if you're a computer scientist. So one of the big things you learn in data structures and different parts of computer science is that you want to have locality in your data. You want to bring data that's similar to each other that you need to work with to be close, so that you can access and compare things that you need to compare and so forth. This breaks a lot of notions of locality. So why would we want to do this? So you're not in the class, you can't answer it.
In case a meteor strikes a bunch of your servers.
Good. Well.
Okay, maybe not a meteor, but
yeah. So there are there's some newer stuff. So now Google has replicas of all of its data, not just in the block structure, but they have replica in entire data centers. People know where most of their data centers are, but they may have some where people don't know where they are, just to kind of replicate these. There are various data centers around the world that are not. They try and keep these a secret because they want to prevent against this sort of attack. There are replicas for asteroids and so forth, or certain attacks on data centers, but that's not what's going on here. Okay, so but that's onto something.
To reduce the bandwidth?
It's for disaster recovery, like if one system goes down, we can access the data.
Yeah, good. So one of the reasons is resiliency. So if you store it all in one computer, it's not uncommon for one computer to crash, right? So I guess not the whole class here, but who's had a computer crash within the last year? Okay, so at least okay, that's more than I expected, but it illustrates my point, right? So if you have your data on 1,000 different machines, probably one of them is going to crash, right? So you don't want to lose that part of your data, right? If you're running a long process that takes a long time on these 1,000 machines, you actually don't want, if it crashes during the process, you need to restart. But if you have 1,000 of them, the chances are pretty reasonable that one of them is going to crash. And crashes do happen, as you've illustrated. I hope it hasn't had to do with this class. So we had a really high number of hands being raised. Okay, so this is a real issue. One is, for prevention of the ultimate loss of the data. What's more happens usually in the runtime is just some the motherboard or something will fail. The data won't be lost, but the computation will kind of get screwed up. So if the data is on a different computer, you can then re-go get the data and not have to wait for the computation and not lose it. There are other backup. So if you do like a RAID backup of a hard drive, it does something very similar to this, where it puts on different hard drives. So what's another reason why you may want to do this?
You want your data to be available at many centers so that it can be processed with less cost. Say, Google has its data center over at many places. So we want that if somebody from US is querying, it should get the data from the data center at US. If somebody from Europe is querying the data, it should get the data from the data center at Europe, not just from. It should not make a request to the US data center.
Yeah, so that's another good point. So if people are querying all around the globe, you want to be able to return an answer from an index that's closer, actually closer to them, right? So that's kind of not what's going on here. We're kind of doing computation of something. We're having all the data is big, but it's still all in one data center. What's really cool about what you said, so actually Google does this itself. It has different versions of its index around the US or around the globe so that you have faster access time. But there's this really cool company called Akamai which does this for smaller businesses, and like one of their big customers is like so I think CNN is still one of their customers. So the CNN webpage is looked at by lots and lots of people. They don't want everyone to have to go to Atlanta to get it from their servers, so they store a local copy. So there are probably 2 or 3 different Akamai servers on campus that store a version of the CNN webpage. So when you look it up, you just have to get to the local server. So Google does that to some extent with its data centers and so forth. That's kind of what's going on here, but at a much smaller level.
If you're trying to do a bunch of computations, then you might want to be able to draw data in parallel, because then you get throttled by network speeds. So if I want to grab a piece of data from a computer, I can only get so much because of the network has limitations to the computer. Or if I distribute it and pull parallel sources, I can get a lot more. So the data is
So the data is redundant. So as you were saying, so we tried to distribute it randomly. So if you have a query, the computation can be done on each of the local machines to try and retrieve it, and the query is spread out across them. But sometimes you're still going to get some collisions where more of the data may end up on one single machine. So then what you could do is say, well, if I have different copies on another machine, so then I can make sure that that I query different blocks from different machines, so I can try and spread the load out a bit more. So also sometimes when you're doing the process, in addition to a node going down, one node may just get really slow. It may have someone's trying to do maintenance on it and it's just running slow, so you can kind of realize it's running slow and switch the computation to another machine that has the same data on it. So then the last reason is heterogeneity. So that means that if not all of the machines in your cluster are exactly the same, some may be slower than others, some may be faster. If you spread it out, you can say, well, I'm still going to ask the slower machine to do something for me, but I'm not going to ask it to do as much. So you can have them so they all finish at roughly about the same time. If you know kind of the relative speeds, which is not hard to figure out, then you can spread out the work in a way evenly, as long as your data is spread out with some of this redundancy in there. So if you ever, I don't know if you ever seen pictures of the first cluster for Google. It was in this. This was before they formalized the distributed file system, MapReduce. But it was in one of the offices in Stanford. And it was a bunch of these motley selection of computers. They were building the search engine and just wanted to build a bigger and bigger one, so they kept adding on different strange machines, anyone they could get a hand on. So they'd all different machines, and all this work partially, one of the ways they got this to work was by, as they were building up the company, was to kind of spread out the blocks in this different way. So okay. All right, so we're ready to actually get to how you actually do MapReduce now that we have it built up. We have the notion of what the data looks like and how the data is stored on this distributed file system. All right, so MapReduce has 3 or 4 steps you need to think about conceptually, but then you only need to worry about 2 of them, just the map and the reduce step, right? So the mapping set is going to take these as input. Take as input these key value pairs, and it's going to output different key value pairs. So typically, it's going to read over whatever data it has stored inside of one HDFS block, and each of these are key value pairs, and it's somehow going to create new key value pairs. Okay, so sometimes it doesn't actually do anything. Sometimes it just takes the original format and it doesn't do anything. But the idea is it's mapping it to a different sort of relationship. It's taking this data and mapping it to a different way. So it may be one key value pair turns into many key value pairs. And the keys and the values may change depending on what is the content in here. So it's typically the key and the value are a function of the original values.
we want to apply MapReduce, do we need to pre-process the data and convert it into key value pairs, or?
So I mean, so it's you typically think of it this way. Often it may be stored as a key and a value, but if your data set is just a value, then it has a pointer coming into it, and that pointer can be the key, right? So if your value is just like a large, like you're storing a document, you have a name of the document, you have a pointer into it, you have a file location for it, that can be the key. So it's just some way of storing the initial data initially on your server some way. So, yeah, so I'll go through some examples. So let me give the structure, but so it kind of, okay, the simplest thing, and I guess we can go through this as a running example, is a problem called word count. And there the goal, the initial key value pair is each key value pair is one document. So the key is the document name, and this is all the words in the document, right? So okay, and so now the goal of word count is to count how many times each word appears in all of your documents. You have a whole corpus, a big set of documents. Okay, and so then what the mapping does is, so let's say the words are actually the words are Sam, I am, right? Then the key value pair mapping would be